All right, let's talk about one of the coolest, most essential tricks in modern chip design. It's called power gating. It's basically the hidden art of shutting down entire sections of a microchip to save power, and today we're going to pull back the curtain and see exactly how it's done.
You've probably noticed this, right? You put your phone down, you're not even touching it. You come back a couple hours later and poof, the battery's dropped. So what's going on? Well, the culprit is this sneaky little thing called leakage power, and it's happening deep, deep inside the silicon.
So before we can really get into the solution, we have to understand the problem. And at the very core of every modern chip, there's this fundamental challenge, the leaky transistor. I want you to imagine billions of microscopic faucets, and even when they're supposed to be all the way off, every single one is still dripping, just a tiny bit. Now, one drip is nothing, but when you have billions of them, this constant tiny waste of energy adds up. It's called sub-threshold and gate leakage, and it's what's draining your battery and, just as importantly, generating a ton of heat.
Now, engineers have a couple of tools to fight this. You might have heard of clock gating. That's a really popular one. It's kind of like turning off the light switch in a room. Sure, the lights are off, the activity stops, but there's still power flowing to the outlets, right? Power gating, on the other hand, is way more aggressive. It's like going down to the basement and flipping the main circuit breaker for that entire room. Boom! It cuts the power off completely, stops all those little drips, and just eliminates the leakage.
So here's the bottom line. When you absolutely need to stop leakage dead in its tracks, power gating is really the ultimate solution. So let's take a look at how it's actually put into practice.
So what is it formally? Well, power gating is just the technique of inserting a special kind of transistor, we call it a power switch, right between the power supply and a whole block of logic. When that block is just sitting there idle, we just turn that switch off. It's that simple. We effectively disconnect it from the power grid.
And why is this such a huge deal? Well, first and most obviously, longer battery life. A massive chunk of your device's energy is just lost to leakage while it's doing nothing. Second, you get cooler chips. All that wasted energy has to go somewhere, and it becomes heat. Power gating cuts that way down, and that leads directly to the third point, improved reliability. See, heat and leakage can feed on each other in this really dangerous cycle, and power gating just steps in and breaks that cycle.
Okay, so we need a switch. Simple enough, right? But where do we put it? And what kind of switch should we use? This brings us to the first major design choice that engineers have to make.
You've basically got two main options here. You can think of it like putting a valve on a water pipe. You could put the valve right at the start. That's what we call a header switch. It uses a PMOS transistor, and you place it between the main power supply, VDD, and the logic block itself. Or you could put that valve at the very end of the pipe. That's a footer switch. It uses an NMOS transistor, and it sits between the logic and the ground connection, VSS.
Now this is where the real engineering trade-offs come into play. It's not as simple as just picking one. Header switches, the PMOS ones, they're actually better at stopping leakage, but they're physically bigger. On the other hand, footer switches, the NMOS ones, they're smaller and they're more powerful for their size, but they tend to leak a little bit more and can cause this nasty effect called ground bounce, which is basically electrical noise that can mess with the whole chip. So the choice really depends on what you're trying to prioritize for that specific part of the chip.
So you might be thinking, okay, it's just one big transistor that we turn on and off. Seems pretty simple, right? Well, in high-performance chip design, it's pretty much never that easy.
In reality, a modern power switch is actually a really sophisticated little piece of circuitry. This diagram shows it perfectly. It's often a multi-stage design. You can see there are two separate gates here, G1 and G2. First, the control logic turns on that smaller transistor, M1. This is what we call the pre-charge path. It just gently starts to power up the block. Then, only after that, the much wider, much more powerful main transistor, M2, turns on to deliver the full current. It's a very deliberate two-step process to make sure the power-up is smooth and safe.
All right, so we get the switch itself now. Let's zoom out and see how these switches are actually laid out across the chip. This gets us into the chip-level architecture.
And again, we've got two main philosophies. Over on the left, you see block-level gating. This is where you group a whole bank of large switches together to service a big chunk of logic. It's simpler to design, but just look at that graph. See that massive spike in the power on current? We'll come back to that. Then on the right, you've got the distributed approach. Here, you pepper smaller switches all throughout the design. It's more complex to implement, for sure, but notice how the power on current is much, much gentler.
And that current spike we just saw? That brings us to the single biggest, hairiest challenge in all of power gating, flipping the switch back on.
See, when you go to power up a block that has been completely off, every single tiny capacitor inside it wants to charge up at the exact same time. This creates this huge, sudden demand for current that we call inrush current. It's like opening the floodgates of a dam. All that current rushing in at once can actually cause the chip's main voltage to dip so low that it crashes the entire system.
Let's look at that spike again from the block-level design. This is the enemy. This is what gives chip designers nightmares. That sudden peak represents a massive surge of current that the chip's power grid has to somehow handle. If it can't, the voltage collapses and your system fails.
So how do engineers tame this beast? Well, the solution is actually pretty elegant. Instead of sending out one massive on signal to everything at once, they create a staggered start. They break the switches up into smaller groups and then turn them on sequentially, one after the other.
And this diagram shows a really common way to do it. It's called a daisy chain. The enable signal doesn't hit all the switches at once. Nope, it comes in on the left, turns on that first column of switches, then that signal propagates through some buffers to the next column, turns them on, and then on to the next one, and so on. By sequencing the power up like this, you turn that violent current spike into a nice, gentle, manageable ramp. It's really clever. So let's just quickly recap. We've seen that leakage is the silent battery killer in all our devices. Power gating is the hardcore fix for it, but it's a whole game of engineering trade-offs. Do you use a header or a footer switch? Do you go with a block or a distributed layout? And we've seen that the true art form here lies in taming that dangerous inrush current, using smart techniques like the daisy chain to safely bring a sleeping part of a chip back to life.
It really makes you think, doesn't it? As we keep packing more and more power into these tiny devices, this complex dance of turning things off and on again isn't just some neat feature. It's absolutely fundamental to making it all work. It might just be the unsung hero that's keeping our gadgets from literally melting down.